There's one big problem with large language model based on the transformer architecture. They're fundamentally wasteful when it comes to computation. So every time an LLM recalls a simple fact, something like Paris is the capital of France, it runs through dozens of transformer layers when it could just look it up like a dictionary. This is the core insight behind DeepSeek's new paper called Engram, and it might change how we think about LLM architecture. So in general, there are fundamentally two different type of tasks that we ask LLMs to do. One is complex reasoning and the other one is simple recall. For complex reasoning, an example could be, why did the Roman Empire fall? That's a hard question. It requires synthesis, weighing evidence, and building arguments. It needs deep computation for that. On the other hand, for questions like who is Princess Diana, you don't really need reasoning. You just need to look up that fact. However, in traditional transformer-based large language models, both of these questions go through exactly the same pipeline. So let's say if you have 30 plus layers of transformers, they're going to do exactly the same computation. This is basically the hidden inefficiency in large language models. They don't distinguish between tasks that need help from deep thinking and tasks that should be instant lookup. The Engram paper from DeepSeek has a beautiful example of this. So watch what happens when LLM processes Diana, Princess of Wales. So this should be simple. You're just trying to identify a famous person. For this theoretical model, the model starts with layer 1 and 2 by first recognizing Wales as the country in the United Kingdom. It's building up context from scratch. Now, layer 3 in this case knows that Wales is in Europe. In layer 4, Princess of Wales, it knows that's a title held by a female sovereign. More specifically, it's the wife of Prince of Wales. Now, finally, layer 6, where it gets to know that Diana, Princess of Wales, along with her date of birth and date of death. In this example use case, 6 layers of neural network computations were used just to reconstruct what could be just a dictionary lookup. This is what exactly happens in transformer-based architectures. So for every named entity, every idiom or common phrases, the model is doing deep computation to simulate what should be a simple memory. Here's where it gets really interesting. So from 2021, a paper by Giva and colleagues, they revealed something surprising about how transformers actually work. So they found that the feed-forward layers in transformers already function like key-value memories. The first feed-forward network layer acts as a pattern detector, the keys, and the second layer projects information into the output, the values. The architecture is already doing memory lookup through computation. Now, think about that. LLMs are using deep computation to simulate hash tables, which raises the obvious question, what if we just gave them an actual hash table? That's exactly what DeepSeek did with this paper. Now, it's called Engram. It's conditional memory via scalable lookup, and it's designed to complement what we already have, not to replace it. Modern LLMs already use something called mixture of experts, or MOE. That's the conditional computation. You route tokens to different experts based on what they need. Now, Engram adds a second access, which is conditional memory. So instead of routing to expert, you do direct lookup into massive embedding tables. So you are getting 2 access of sparsity. One is for computation for reasoning and memory for recall. Now, the beauty is that it directly maps to what language actually contains. Some dependencies are compositional. For example, why did the stock market crash? You need to reason about cause and effect. This is dynamic, context dependent, and you get novel combination every time. So you actually need to do deep computations. But other dependencies are static patterns. For example, if you say Diana, Princess of Wales, Alexander the Great, or even phrases, by the way, these are local stereotyped frequent. They don't change based on the context. So it should be an instant lookup. And the Engram's insight is simple. Match the mechanism to the task. Don't use deep computation when a lookup will do. Now, here is how Engram works. So let's say you have an input, Alexander the Great. First, you extract n grams. In this case, we're going to extract 2 grams and 3 grams. Grams basically are the combination of different tokens that you can extract from a given phrase or sentence. Now, these get hashed, you're going to actually result in multiple hash, and that's important for avoiding collision. These hashes point to a massive embedding table. We're talking billions of parameters here, but they don't require computation. It's a simple lookup. So you retrieve embeddings based on those hash lookups. But here's the most critical part. Before those embeddings get used, they pass through a context-aware gate. So the gate looks at the model's current hidden state and decides, does this retrieved memory actually make sense in this specific context? So if it does, the gate opens and memories flow through. If it doesn't, the gate suppresses it. Okay, now let's look at the context-aware gating mechanism. The gating mechanism deserves more attention because hash lookup can be wrong. So for example, what happens when two different n-grams hash to exact same slot, or when a word has multiple meanings? Okay, so let's look at these two different scenarios. So on the left-hand side, the model retrieves Apple Inc. and the context is a tech company stock. So the gate checks, does the retrieved memory align with the current context? If yes, the gate is going to open. Now, on the right-hand side, we have exactly the same phrase, but the context is fruit salad recipe. So that doesn't match at all. The gate closes, and this wrong memory gets suppressed. So this is how Engram handles words with multiple meanings. The gate uses the model's understanding of context to filter what goes through. This lookup can be extremely fast, and you don't need that many computations. But how should you split your parameters between MOE and n-grams? So this paper found a U-shaped curve. If you allocate everything to MOE, 100%, that's suboptimal. According to them, you are wasting depth on static parameters or patterns. Now, if you go too far to the other direction, too much memory, not enough computation, you lose reasoning capability. According to this paper, the sweet spot is between 70 to 80% of parameters to MOE and 20 to 25% parameters to n-gram. This U shape is actually really important. It confirms that you need both. The optimal architecture has both working together. Okay, but does it actually work? Let's look at some numbers. Now, in this case, they compared Engram 27B against a pure MOE 27B. They had same parameters, same computational flops, same training data. The only difference is the architecture. And they used the optimal distribution between the MOE and Engram as we discussed before. Okay, so knowledge tasks improved. For example, MMLU up 3 points. Chinese knowledge was up 4 points. Now this makes sense. You would expect a memory lookup to help with knowledge. But I think the most surprising part was that the reasoning capabilities also, one reasoning benchmark went up by 5%. The ARC AGI went by 3.7%. And you also had improvements in human evolve, which is a code benchmark, as well as mathematics. Okay, now if you look at this, you would say that reasoning improved more than the knowledge. That's backward from what you would expect if it's a good knowledge lookup. But in this paper, they have an explanation of why this happens. And the reason that they think the reasoning got improved is because the model effectively got deeper. Although you have the same number of layers, but functionally, it's a deeper model now. But in order to understand this, let's think about what exactly happens in a pure MOE. So for this specific example, the first 6 or so layers are consumed by static reconstruction. So the model is trying to figure out Diana, Princess of Wales, refers to a specific person. That's not reasoning, it's just memory lookup. But still, the MOE has to go through all those computations. Now, in case of the Engram model, that reconstruction happens through O of 1 lookup. The memory is handled before the computation even starts, which means all the 30 layers are now available to actual reasoning. The paper confirms this with the CKA analysis. So layer 5 of the Engram produces representation equivalent to layer 12 of the MOE baseline. In this case, the model is getting more reasoning done per layer because it's not wasting layers on reconstruction. They also have some interesting results when it comes to long context performance. So by handling local dependencies through Engram, attention is freed up for something else. So look at these numbers. These are massive improvements. Again, the mechanism is straightforward. Ngram patterns are local dependencies. When Ngram handles those, attention does not have to. And the attention is now free to focus on long-range dependencies. That is, things that are happening far apart in the context window. There are some other interesting findings in this paper, especially when it comes to DeepSeek. You need to talk about hardware story as well. This is where the original DeepSeek models blew up with the R1 series. Okay, so the first thing is that MOE routing is dynamic. You don't know which expert you need until you have computed the hidden states. That creates communication bottlenecks. On the other hand, Ngram lookup is deterministic. The Ngram IDs from the input tokens alone before any computation even happens. So this enables prefetching. While the GPU is computing layer 1, the CPU can already be fetching Ngram embeddings for layer 2. And the communication is hidden behind the computation in this case. The result, less than 3% throughput penalty for 100 billion parameter table sitting in the host RAM. We're not talking about using the GPU memory. We're using regular system RAM for lookup. This is incredible. Now, this is a very interesting approach, which I think is going to have real implications. But let's talk about limitations, because this isn't magic. So one of the biggest problems with hash lookups is hash collisions. Multiple Ngrams can map to the same slot. Now you have multi-head hashing and gating, which could potentially mitigate this, but they don't eliminate it completely. The second problem is static embeddings. So unlike neural parameters, these don't adopt during training. Now the gating mechanism does provide some compensation for it, but it adds complexity. Then you have limited Ngram order. The paper uses 2 Ngram and 3 Ngram. Patterns, for example, 4 or 5 Ngram might not be captured. Now, it's very important to think that even though we're doing lookup, this is not RAG. So Ngram does not connect to external knowledge bases. These lookup tables needs to be constructed during the training process. And it's also not dynamic memory. So embedding encode patterns from training that don't update at inference time. And also, we don't know how it's going to perform in highly specialized domains. The paper attests journal benchmark. Specific domain-specific performance is still an open question. Okay, so let's take a step back and think about what exactly does this mean. At its core, this paper is about separation of concerns, which means don't use the same mechanism for everything as it's been done today. And this actually mirrors how human cognition works. So we're talking about system 2 thinking is slow and deliberate, just like mixture of experts or deep reasoning system. Now, system 1 thinking is fast and automatic. That is going to be like Ngram, where you are doing instant pattern recognition. There is a theory that human cognition has this dual structure. Maybe LLMs need the same thing. Now, before transformers, sequence models like LSTMs, RNN, struggles with long-range dependencies. Then attention was introduced and it changed everything. By the same token, what if this conditional memory is another missing primitive? What if we have been building LLMs without a fundamental capability that they need? I think if this actually pans out, the implications are going to be significant. For memory efficiency, you use the same compute for better results or same results for less computation. Either way, you're getting more out of your training budget. Now, for hardware economics, I think 100 billion parameter in a host RAM with less than 3% overhead, which is not using GPU memory, is going to be pretty awesome, because you're creating and storing this knowledge in regular system RAM, which is much less cheaper. So this could reduce the barrier to deploy larger models. And I think for architectural research, this opens new directions. So conditional memory alongside conditional computation are going to be the two axes of sparsity. Now, for DeepSeek specifically, they might go and use this on large scale for something like DeepSeek V4 or R3. Okay, so here is the core insight. LLM have been using computation to simulate memory because transformer architecture lacks a native lookup primitive. It's like using a calculator to store phone numbers. It works, but it's wasteful. Ngrams, on the other hand, gives LLMs an address book, and these results suggest that this was something they needed all along. I'll put links to the paper and the code in the description. Okay, so this is it for this video. I'm going to be trying to create these deep dive into technical content. And if you found this video useful, please subscribe. And if you have any questions, put them in the comment section below. Thanks for watching. And as always, see you in the next one.